Hi guys, welcome again to another one of these videos. I'm not going to number them because they're all a little bit out of order at the moment, and I want to make sure that you get the full sequence, and they will be sequential, but some of the numbering may change as we go along. Um, so basically this one is going to focus on acid-base equilibrium. So we've kind of looked at equilibrium systems already, and the main thing when we're looking at acid-base equilibrium is that when an acid is not a strong base, so when we're talking here about the fact that many acids are only partially ionized in water, what we're talking about is ones that are weak. So weak acids only partially ionize in water because strong acids will fully ionize and therefore will not reach an equilibrium. But weak acids only partially ionize in water, and we do have a grading scale for acids. So the stronger they are, okay, make sure we're using the terms strong and weak. Stronger they are, the more readily they are ionized, and the weaker they are, the less they're ionized. So provided the ionization doesn't go to completion, you have an equilibrium which exists between the acid molecule, so this is the acid molecule, and its constituent ions. And most of the time we're going to be looking at the H plus ions, mainly because, and again, remember that H plus ions is equivalent to a hydronium ion, all right? And that's because that's what affects the pH of the solution. So we will find changes that occur relate to the concentration of the H plus ions. Obviously, if the equilibrium lies to the right, then we have a large number of these ions. And if the equilibrium lies to the left, then we have a smaller number of ions. And therefore, the degree of ionization is directly related to the pH. Now, there's a mathematical relationship here which we don't need to worry too much about, but you may see references to this equilibrium constant, Ka, which is the acid ionization constant. And it's something that we need to use in order to describe exactly where an acid falls in terms of its degree of ionization. So strong acids will have a very high Ka value, and weak acids will have a much lower Ka value. So this isn't something that's critical to remember. It's simply something useful to contextualize our understanding. This is how Ka works. Ka is equivalent to the concentration of the products, which is the two ions, divided by the concentration of the reactants. And when we're looking at each of these two, we are talking about concentrations. So we just need to make sure that we are realizing that. And so, and these are multiplied together. Okay, so we multiply the concentration of H plus ions by A minus ions. And generally speaking, if the acid is a monoprotic acid, these two will be equal. So if this is X, then this will also be equal to X. Okay. And then the HA concentration will be whatever the initial concentration was, minus presumably X if the ratios are 1 to 1 to 1. What this means is that if the value of Ka is small, then it's a weak acid because the concentration of products will be small and therefore the reactants will be large. Okay, so this is a Ka small. And of course, if the products are large and the reactants are therefore small, then the Ka value will be large. So this is the only reason I talk about this now is that there is a mathematical relationship, not one that we need to calculate, but one that will be quite useful, particularly when we look at how water behaves during different types of reactions. So here's a practical question then for you. It came out of the HSC in 2013. If an indicator is placed in water and the resulting solution contains a green anion, IND, this will be an anion, so effectively an A minus, and a red molecule, HIND. So IND is just being used to represent the indicator. Explain why this solution can be used as an indicator. So use of an indicator is related to color change. Okay. If a solution is to be effective as an indicator, then it must change color in the presence of an acid or a base. And if we're going to look at how effective this is as an indicator, then we're going to need to include a suitable chemical equation. So a suitable chemical equation would be H indicator, okay, which is the version of the molecule, and that will be in an equilibrium with H plus ions and IND minus ions. This is red, and this anion over here is green. Okay, so what this means is that when we are adding, so if it's going to be an effective indicator, then we need to add either base, so plus base, or plus acid. And then you will need to explain what happens to each of these as you are identifying what you're doing. Okay, so if we add a base, effectively what we're going to do is use what we are now aware of as the Arrhenius definition, and that is the addition of OH minus ions. So we're going to add OH minus ions. Okay, either way, the base is going to attack this species here. Okay, so the hydrogen ion concentration is going to drop. Le Chatelier's principle says it will shift in order to counter that change, and therefore the solution will become greener. Likewise, if we add an acid, what we're usually doing is adding H plus ion, so the H plus ion concentration will increase. So again, it's this species over here, it will increase. If it increases, then the Le Chatelier principle says shift to the equilibrium in order to counteract the change, which means it's going to go in this direction, and we're going to end up with a solution that is becoming more red. Something that's in the middle, you presume, will have equal amounts of maybe red and green, and so will be some intermediate color between red and green. Thanks for listening.